In 1971, Donald Lynden-Bell dropped a bombshell that reshaped the cosmos. He claimed a dead, invisible monster lurked at the heart of our own galaxy. The strangest part? He figured it out by solving the mystery of quasars, objects so bright they shouldn't exist. Quasars, discovered just 7 years earlier in 1964, poured out energy equivalent to 1 trillion suns from a region smaller than our solar system. No known star could produce that kind of power. Lynden-Bell, a British astrophysicist at Cambridge, realized the only engine violent enough was gravity itself, matter screaming down into an abyss so deep that light could never climb back out. In a landmark paper co-authored with Rees, he argued that quasars were the furious youth of supermassive black holes, and that a dormant version of such, a beast, likely sat silent at the center of the Milky Way. Most astronomers dismissed the idea as too extreme. Black holes were still theoretical curiosities from Einstein's 1915 general relativity, mathematical ghosts on paper. Carl Schwarzschild had found the first exact solution to Einstein's field equations in 1906, describing a point of infinite density where space-time collapses, but no one had ever seen one. The idea that our own galactic neighborhood harbored a black hole millions of times heavier than the Sun seemed like science fiction. Yet the evidence from quasars was undeniable. Something had to power them, and general relativity provided the only viable mechanism. Lynden-Bell and Rees proposed that a black hole of roughly 1 million solar masses sat at the center of the Milky Way, its presence betrayed only by the frantic motion of stars orbiting an invisible point in the constellation Sagittarius. The challenge was proving it. You cannot see a black hole directly, it swallows light, not emits it. But you can see its gravitational grip. If a black hole sits at the center of a galaxy, stars near it should whip around at impossible speeds, like planets orbiting a star you cannot see. The trick was to watch those stars over years, decades, tracking their motion with enough precision to calculate the mass of the invisible object pulling on them. In the 1990s, 2 rival teams took up the hunt. Reinhard Genzel, at the Max Planck Institute for Extraterrestrial Physics in Germany, turned the telescopes of the European Southern Observatory toward the Galactic Center. Andrea Ghez at UCLA used the Keck Observatory in Hawaii. Both teams pointed their instruments at the same patch of sky, 26,000 light-years away, and waited. What they found defied belief. Stars near the Galactic Center moved at thousands of kilometers per second, so fast that a single orbit took only 16 years compared to our Sun's 230-million-year lap around the galaxy. One star, designated S2, passed so close to the invisible object at its closest approach in 2002 that it reached nearly 3% the speed of light. By tracking these orbits over decades, Genzel and Ghez independently calculated the mass of the unseen body, 4.3 million times the mass of our Sun, all crammed into a region no larger than our solar system. The only object in physics that can pack that much mass into that small a volume is a supermassive black hole. In 2020, the Nobel Prize in Physics recognized their work, half to Roger Penrose for proving black holes are a real prediction of general relativity, and half, jointly to Genzel and Ghez for proving one actually sits at the center of our galaxy. But the discovery raised a far deeper question, one that still has no answer. The question that emerged from Genzel and Gez's observations was not whether supermassive black holes existed. That was settled. The question was why they sit at the center of every large galaxy. And that question led astrophysicists to a correlation so tight it felt like a conspiracy. In the late 1990s, as Hubble Space Telescope data accumulated, astronomers noticed something strange. The mass of a galaxy's central black hole was not random. It was precisely proportional to the speed of stars moving in the galaxy's central bulge, a relationship now called the M-sigma relation. If you measured how fast stars jostled around in the crowded core of a galaxy, you could predict the mass of its hidden black hole to within a factor of 2. The correlation held across galaxies of all sizes, from dwarfs to giants. This was not coincidence. This was evidence of a conversation between the black hole and its host galaxy, a feedback loop that shaped both. The mechanism, as theorists later worked out, is brutal and elegant. When gas falls toward a supermassive black hole, it does not simply disappear. It heats up to millions of degrees, releasing radiation so intense it can outshine every star in the galaxy combined. That radiation pushes outward, heating and expelling the surrounding gas. And gas is the raw material from which new stars are born. So when the black hole feeds too aggressively, it effectively chokes off its own food supply and simultaneously shuts down star formation across the entire galaxy. The black hole and the galaxy grow together, locked in a violent, self-regulating dance. The bigger the galaxy's bulge, the more massive its black hole must be to keep the system in balance. But this raised another problem, one that has haunted theorists for decades. Black holes do not just appear fully formed at the centers of galaxies. They must grow from seeds, and the early universe did not give them much time. Observations from the James Webb Space Telescope, launched in December 2021, have revealed quasars powered by supermassive black holes existing less than 700 million years after the Big Bang. Some of these black holes already have masses of 1 billion suns. How did they grow so fast? Standard accretion models, gas slowly spiraling inward, cannot explain it. There simply was not enough time. This is where the theoretical bottleneck known as the final Parsec problem becomes critical. When two galaxies merge, their central black holes sink toward the center of the new combined galaxy. Initially, dynamical friction, the gravitational drag of passing stars and gas, slows them down and brings them together. But at a distance of about 1 parsec, roughly 326 light-years, that friction stops working. The black holes stall, orbiting each other at that distance, unable to lose enough energy to merge. Without a merger, they cannot grow into the supermassive giants we observe. For decades, simulations showed black holes getting stuck at this final parsec, and theorists had no good explanation for how they escaped. The leading hypothesis today involves a third body. If a third supermassive black hole or a massive clump of gas falls into the galactic center, it can gravitationally slingshot the binary, stealing energy and allowing the pair to finally spiral together. But this requires a constant influx of material, which is not guaranteed. Another possibility proposed in recent years is that dark matter might interact with the black hole binary in ways we do not fully understand, draining orbital energy through friction with the dark matter halo itself. Neither explanation has been confirmed. The final parsec problem remains one of the most stubborn open questions in theoretical astrophysics. What is clear is that supermassive black holes are not cosmic afterthoughts. They are architects. They regulate the growth of galaxies, determine how many stars form, and influence the distribution of matter across cosmic scales. Without them, galaxies would look radically different, messier, more chaotic, possibly barren of the conditions that gave rise to life. The black hole at the center of the Milky Way, Sagittarius A, with its 4.3 million solar masses, has been quietly shaping our galactic home for billions of years. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A, a fuzzy orange ring of light surrounding a dark shadow. That image, captured by a network of 8 radio observatories spanning the globe, showed the silhouette of the black hole itself against the glow of superheated gas falling into it. For the first time, humanity saw the face of the monster Lynden-Bell had predicted 51 years earlier. It was exactly where he said it would be. The image was a triumph, but it also deepened the mystery. How did these objects form in the first place? The leading theory today posits 2 distinct paths for the seeds of supermassive black holes, and the debate between them has split the astrophysical community. The first path, known as the light seed scenario, suggests that the first generation of stars, called population II stars, were enormous, perhaps hundreds of times the mass of our Sun. These giants lived fast and died young, collapsing directly into black holes of perhaps a few hundred solar masses. Over cosmic time, through mergers and accretion, these seeds could grow into the monsters we see today. But there is a problem. The math does not quite work. To reach 1 billion solar masses in under 1 billion years, a seed black hole would need to consume matter at an implausibly constant, voracious rate, a feast that never slows down. The alternative is the heavy seed scenario, and it is far more dramatic. In the early universe, massive clouds of primordial gas, hundreds of thousands of times the mass of the Sun, may have collapsed directly into a black hole, skipping the star phase entirely. This would produce a seed of perhaps 100,000 solar masses right from the start, giving it a massive head start on growth. The James Webb Space Telescope, with its infrared eyes piercing the cosmic dawn, has found candidates that favor this heavy seed model. In 2023, a team analyzing JWST data identified a galaxy from just 570 million years after the Big Bang that hosts a black hole of 40 million solar masses. That is too large, too early for the light seed model to explain comfortably. The heavy seed hypothesis suddenly looks more plausible. But even if the seeds are heavy, they still must merge to grow. And that brings us back to the final Parsec problem. In 2023, a team of researchers at the Flatiron Institute in New York published a breakthrough simulation. They showed that the key might be the shape of the galaxy itself. If the merging galaxies are not perfectly spherical but have irregular, clumpy distributions of stars and gas, the gravitational chaos can torque the black hole, binary, draining angular momentum more efficiently than previously thought. Their simulation demonstrated that in realistic, messy galaxies, the binary can cross the final parsec in just a few million years, a blink of an eye on cosmic timescales. The problem may not be as intractable as it once seemed, yet another possibility has emerged from a completely unexpected direction: gravitational waves. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the first ripples in spacetime from merging stellar mass black holes. But supermassive black hole mergers produce gravitational waves of much longer wavelengths, waves that take years to complete a single cycle. To detect these, astronomers are now building a different kind of observatory, pulsar timing arrays. By monitoring the precise tick of dozens of rapidly spinning neutron stars across the galaxy, scientists can look for the faint jitter caused by passing gravitational waves from supermassive black hole mergers. In June 2023, the North American Nanohertz Observatory for Gravitational Waves, NanoGrav, announced the first evidence of a background hum of these waves, a murmur that likely comes from hundreds of thousands of merging supermassive black holes across the universe. The signal is still too faint to pinpoint individual mergers, but it confirms that these events are happening. The final parsec is being crossed somewhere out there. What this means is profound. Supermassive black holes are not static monuments at the centers of galaxies. They are dynamic, growing, merging entities that have been shaping the universe since its infancy. The M-sigma relation now appears to be a fossil imprint of this coevolution, a signature left behind by billions of years of feedback, mergers, and gravitational chaos. Every large galaxy, including our own, carries this scar at its heart. The black hole is not an intruder. It is part of a galaxy's identity, as intrinsic as its spiral arms or its globular clusters. The deepest question remains unanswered. Which came first, the galaxy or the black hole? Did the black hole seed the formation of the galaxy by gathering gas around it? Or did the galaxy form first and later grow a black hole at its center? Current simulations suggest both paths are possible, and the answer may depend on the epoch and environment. In the early universe, heavy seeds may have formed first, acting as gravitational anchors around which the first galaxies assembled. In later epochs, galaxies may have merged and funneled gas into their centers, growing black holes as a byproduct. The truth is likely a hybrid, a cosmic dance where neither partner leads, but both respond to each other's moves across billions of years. The Event Horizon Telescope image of Sagittarius A in 2022 did more than confirm a prediction. It opened a window into the violent ecology of galactic centers. That fuzzy orange ring was not the black hole itself, but the shadow of its event horizon cast against superheated plasma swirling at relativistic speeds. And that plasma told a story. By analyzing its polarization, the orientation of light waves as they bent around the black hole's immense gravity, astronomers could map the magnetic field, lines threading the accretion flow. What they found was organized, structured, and surprisingly strong. The magnetic fields near Sagittarius A are not chaotic tangles. They are coherent, helical structures that can launch jets of particles at nearly the speed of light, punching through the galaxy like cosmic fire hoses. These jets are not unique to the Milky Way. The first image the ET ever released, in 2019, was of M87, the supermassive black hole at the center of the giant elliptical galaxy M87, 55 million light-years away. M87 is a monster. 6.5 billion solar masses, more than 1,000 times heavier than Sagittarius A, and it shoots a jet visible across intergalactic space, extending 5,000 light-years from the galactic core. The 8th image showed the base of that jet, rooted in the black hole's magnetic field. The mechanism, known as the Blandford Znajek process, proposed in 1977 by Roger Blandford and Roman Znajek, describes how a spinning black hole can extract rotational energy from its own ergosphere, the region where space-time itself is dragged along, and channel it into electromagnetic outflows. The black hole is not just a gravitational sink, it is an engine. This changes how we understand the role of supermassive black holes in galaxy evolution. The energy pumped into the surrounding galaxy by these jets can heat the intergalactic medium, preventing gas from cooling and forming stars. In massive elliptical galaxies like M87, the black hole's feedback keeps the galaxy old, red, and dead, a stellar cemetery where new stars are rarely born. In the Milky Way, Sagittarius A is relatively quiet today, but it was not always so. Evidence from Fermi Gamma-ray Space Telescope observations in the 2010s revealed two enormous bubbles of gamma-ray emission extending 25,000 light-years above and below the galactic plane. These Fermi bubbles are likely the fossil remnants of a past outburst from Sagittarius A, a burst of energy that occurred just a few million years ago, a blink. In geological time, our own black hole has awakened before. It will awaken again. The question of why supermassive black holes sit at the center of every large galaxy now has a sharper answer. They are not passengers. They are the engines that regulate the galaxy's life cycle. The M-sigma relation is the fingerprint of this regulation. When a black hole feeds too aggressively, its feedback heats the surrounding gas, shutting down star formation and starving itself. When it is quiet, gas can cool, stars can form, and the galaxy grows. The system oscillates between feast and famine, and the black hole is the governor. Without it, galaxies would either burn through their gas too quickly, becoming barren, or never form stars efficiently at all. The black hole is the thermostat of the cosmos. The most dramatic confirmation of this feedback loop came from observations of a galaxy cluster called Perseus, 240 million light-years away. In 2003, Chandra X-ray observatory images revealed vast cavities in the hot X-ray emitting gas that fills the cluster. These cavities are bubbles blown by the jets of the central black hole in the galaxy, NC 1270. The bubbles rise buoyantly through the cluster gas, heating it and preventing it from cooling. The black hole is not just affecting its own galaxy, it is regulating the temperature of an entire cluster of galaxies, a structure containing thousands of galaxies spread across millions of light-years. The reach of a supermassive black hole extends far beyond its immediate neighborhood. The puzzle is this. If supermassive black holes are so effective at regulating their host galaxies, Why do some galaxies appear to have no black hole at all? In 2024, a team using the Hubble Space Telescope reported that the galaxy NC4649, a massive elliptical, shows no evidence of a central black hole above a few million solar masses, far smaller than the M-sigma relation would predict for a galaxy of its size. Either the black hole is hiding, or the relation is not as universal as we thought. Other galaxies, particularly diffuse dwarf galaxies, seem to lack central black holes entirely. This suggests that the M-sigma relation may only hold above a certain threshold, perhaps around 10 million solar masses, and that smaller galaxies may form and evolve without a black hole governor. The universality of supermassive black holes may not be universal after all. The implications are staggering. If some galaxies lack central black holes, then the black hole is not a necessary condition for galaxy formation. It is a consequence of a particular evolutionary path, one that most large galaxies followed, but not all. The question then becomes, what determines whether a galaxy grows a supermassive black hole? The answer may lie in the early universe, in the density of the primordial gas clouds that seeded galaxy formation. Dense, massive clouds collapse directly into heavy seeds. Diffuse, smaller clouds may form stars first and never concentrate enough mass at their centers to create a black hole. The galaxy becomes a collection of stars without a dark heart. This brings us to the frontier of current research. The James Webb Space Telescope, in its first 3 years of operation, has identified hundreds of galaxies from the first billion years after the Big Bang. Many of them show signs of active black holes, quasars, and accreting giants at unexpectedly early times. But Webb has also found galaxies that appear to be completely passive, with no central black hole activity whatsoever. The diversity of the early universe is far richer than anyone predicted. The story of supermassive black holes is not a single narrative. It is a branching tree of possibilities, where some seeds grow into monsters and others wither into nothing. The final piece of the puzzle may come from gravitational waves. The Laser Interferometer Space Antenna, LISA, a space-based gravitational wave observatory scheduled for launch in the mid-2030s, will be sensitive to the mergers of supermassive black holes in the mass range of 100,000 to 10 million solar masses. LISA will hear the ring of space-time as these giants spiral together, giving us a direct census of black hole mergers across cosmic time. Combined with Webb's images of early galaxies and the EATS images of nearby black holes, LISA will complete the picture. We will know not just that supermassive black holes exist, but how they were born, how they grew, and how they shaped the galaxies we see today. The universe is not only stranger than we suppose, it is stranger than we can suppose. The black hole at the center of our galaxy, silent and patient, has been waiting for us to understand it. We are just beginning to listen.